Last time when I left you, I said the very complex nature of packaging has now moved on into the more sophisticated professional domain where trained engineers or packaging specialists are needed for carrying out the function. So, I'll start with the usual things what you know. This mouse looks relatively innocuous and simple. Actually, a tremendous amount of effort has gone into it, including the smallest thing is about a battery. Actually, it's a cell, a single cell is a battery. So, you see here that every small detail has been taken care of very carefully, and perhaps you will notice, you see this small dock here. This is where we park the RF receiver, and then because of various constraints, in a very peculiar way, it is kept at an angle. This has been inserted at an angle, and then you have the actual sensor and these things slightly offset. Next time, I'll bring you a mouse which will open and show you. And then they have also included a switch, though it has a sleep function. And then other side, if you see, tremendous amount of detailing beyond belief. Just like you have doctors without borders, we have, and the thing is, everything fits miraculously and it works. I thought I'll now introduce you to a little bit of this stuff which we call CAD. Don't worry, it doesn't seem to work. We'll start here everything. Now, like so many other lectures in the academic field which talk a little about anything, including engineering materials, including simple thing like what an LED is, light emitting diode is, the scope is very vast. And often we end up with things like, can there be a blue LED, which of course includes physics and all that, and then eventually some answers, and then the teacher knows the right answer, and then you set a question paper, and then you see at least whether the person who has gone through it has understood a few of the things. The underlying thing at the back is the approach is more appropriate than the correct answer and precision. Now, in the case of our packaging, things have changed a little. The constraints are known, the evaluation criteria are known, but the solutions are not the same. No two solutions are same. I have given you an example of a mouse here. Suppose somebody were to write a book about how to design a mouse, and then he'll tell you here, the person will tell you this sensor has to be here because that gives a, mental image and all that. It is true to a certain level. Beyond that, a lot of it is because of the production constraints. This is where computer aided design gets its features and so on. Now, if you look at my presentation, I am going to tell you a little about CAD, not everything about CAD, and this is not about how to design a CAD package or anything. It is about saying what is available out there, and then one example of some GIF animation I would like to show you. Now, going back to the next slide, the reference I have given at the bottom, saying this is where I have taken it from, but I want you to read the original and also read it along with me. In principle, CAD should be applied throughout the design process. See that you start and go all the way up to the end. So it looks like where relatively established good known products are there. A simple example could be a mobile phone, or even the mouse has changed quite a lot, because if I show you another mouse where the thing is, the whole thing is different. But when you are doing creative design, you start with imprecise representations, sketches, which are tough. It is not easy for us just like that to make a sketch, though several sketch softwares are there, and then in fact I have a graphic pad which is used by illustrators so that we can make things and all that. This illustration software goes to input the start of the remaining design software. So my slide will show you that there are some new software programs currently available which are trying to fill this niche. It remains to be seen how effective they will be and how widely they will be implemented. Reality is, I have seen both. I have seen some people which who go about, designers who sketch on these what do you call, almost like a white paper but on a screen, and then eventually they are part of the team, they move on to the next stage. This is a little boring and dull, but then you can always get back and read it once again. So these are around 20 or 25 slides, and I want you to just read it along with me. Computer-aided design was introduced in the late 60s to expedite engineering drawing. By definition, the word design here probably meant not analytical design, but more a little about drawing. So we have a small what do you call, semantic, I won't call it an issue, small change in semantics. Computer-aided design is also meant for doing analytical design of a known configuration. You have a known configuration, now you do an analytical design, and then you make sure that these there won't be any surprises when the product is made. First of all, it will not be under designed, something need not break. Similarly, it is not wastefully over designed. Got my point there? Analytical design is critical, but in the case of our thing, it's a lot to do with simple geometry. So one example of the geometry and all that I have worked out, I'll show you. When CAD is used mainly in engineering drawing and construction, it can be used for other purposes. So in this case, our packaging still has a lot to do with engineering drawing and things related to fabrication. And the moment the drawing goes to fabrication, from there it goes to eventually computer-aided manufacture. While originally drawings were only about taking a drafting board, drafting machine, and then maintaining that things are in proportion to scale and all that, eventually they have moved over to the shop floor. And in a parallel, I won't call it universe, in a parallel effort, the moment injection molding came about, part of these drawings were also being used by injection molding people. Then suddenly you will notice that traditional engineering drawing, where you have 3-view representation, had its place, had its day, and even today old drawings continue to be made like this. But as you move on, you notice that we have entered the world of 3D, and you create a 3D entity or a 3D object and then try to extract the views and the dimensions back with it. So obviously, like all other any computer automated thing, it is all about how to expedite. Seen this, no? Oh, sorry. How to expedite the engineering drawing process, make it faster. So if it's a thing like a engineering building, so obviously certain details to be added and then they are repetitive. Simple example I can give you are the doorways and window frames and so on, and hardware related to plumbing, hardware related to electrical safety, and then certain norms about egress and ingress into the building. How do you get out in case of emergency and all were easy to check if it was kept on a CAD. Eventually, it all moved on to so many types of CAD are available. So, some of these they have been taken from two sources. So, both of them are, one is I have acknowledged in the first slide, the second one eventually I will show you. It is from the mechanical engineers, some handbook and so on. Originally, the very earliest thing was so-called two-dimensional CAD. Is the pioneer of CAD software and was developed in the 70s. Major auto, aerospace and other companies developed in-house tools to automate repetitive drawing. 2D CAD relies on basic geometric shapes like lines, rectangles, circles to produce flat drawings. These types of software have been first developed way back in the 70s. Autodesk is one of the pioneering companies that has played a significant role in developing this software. But it doesn't mean they're the only persons. The others, these people probably know they released it, others are also having a thing, but by definition, no, in-house. Next, very large thing is the three-dimensional CAD. Is a step up from 2D software of years. As the processing power of computers increased and the graphic display capabilities improved, 3D CAD has become increasingly popular design tool. Understood? No, we have two things here. The word design is used as both something which aids in drafting as well as something which aids in 3D design thinking. Saying can we play around with all the entities and can rearrange them. 3D allows creation of images that are realistic. There are 3D models as they can be viewed and rotated in any direction, X, Y or Z. You can display views such as isometrics or perspectives. Any angle using 3D CAD, 3D CAD tools were introduced in 80s between so many other companies. So, at the end there is a big list of these things. So, we have Siemens, we have Dassault and then we have of course Autodesk's own thing, and it will show you so many things. The rapid advancement of 3D software has helped quick turnaround in product design, giving birth to the concept of full product life cycle management. So, we have Unigraphs NX, Solid Edge, then SolidWorks are all available which will do anything you want. Product design doesn't start and end with making a file. I suggest before you listen to my version of what PLM is, read up, just type PLM software and see what is the application and all. It's slightly beyond the scope of what I am going to talk now. Here comes the very interesting this thing about it, saying simple wireframe models. They create skeleton-like models with lines and arcs. Since they appear to be made of wires, everything in the background is visible. They are called wireframe. They are not very popular anymore, but in the initial stages it made sense because it follows a little like our what do you call school classroom representation. If somebody were ask you to make a cuboid or a parallelepiped object, what will you do? You will try to draw 4 lines representing the top surface and then extend the vertical edges and draw something more which are joined in the front. The invisible ones are put in dots and you can give. This is a very easy way of this thing. First time when you are taught how to draw, you are very happy. You won't understand what a dotted line. In due course, this is stuck, or it's retained in the brain. So intuitively when somebody asks you to draw, you will probably draw with the visible lines all in the front and then dotted lines to show how the back is. Works, no problem at all. But imagine if you are to take a cube and then see it exactly in one isometric view, you will end up with a fantastic hexagonal representation. Very difficult to make out. You will have a trapezoidal thing there, another trapezoid there with something joined here. You will be wondering what the object is. So this stuff came about saying it's not that convenient as we do. Now if you take that object and try to project it, it still did not appear so good. Surface models are slightly better to the extent that in real life when you see an object, for example, I will show you this wireless device I have. What you see here is a surface, and which I have pointed out to earlier, though it is a dark colored object, white highlight has been captured. You have seen here. You have see a beautiful highlight has been captured here because of light shining, and then the moment you have a circular where two edges meet, where there is a cylindrical surface is formed, the surface properties make it appear. You have seen here in this object, it is there. Only it was, if it were a completely black non-reflecting surface, then you may not be able to make out and what it is. So here a surface modeler, like if you have a complex surface like this, in reality you can't make out. So if you see some of those gag TV shows or funny TV shows, sometimes they give what looks like very light this thing, and then inside they would have put a brick or something, and then suddenly when they let go of it, it falls. Alternatively, they take something which is really light and an actor acts as if it's a heavy object, and then when they give it to you, you suddenly feel that there's something missing in it. The important thing about a surface modeler is it's still a collection of surfaces with the edges kept close together, and if you are lucky and if the CAD package interprets it properly, it looks a little like an object. But you should remember, all computers still have a precision while they try to put things together. So sometimes the edges do not get welded, then you can see through the things. Let me pass this, not about the thing, it only like to tell you that it looks like a proper thing. Solid models are considered to be the most useful. They appear to be the same as surface, except they have additional properties like weight, volume and density, just like actual physical objects. See, this is where you have the nice option of making prototypes which are really real, to the extent of some Illustrator software take these things and make it what you call photorealistic renderings, and in some places it is possible. Simplest one talk about is maybe if you have a rod and you have two weights, during calculation we can optimize the design of the other points depending on these weights and depending on the properties of the materials. Again, coming back to the earlier you see here we have from this engineer's handbook beautiful things are there. We have simple 2D drafting, technical illustration. You see here the word illustration is used. Illustration is something which you write down and all that. Technical illustration talks about encoding whatever normally you do. This is what engineers continue to use. So, several places in examinations and all, they will give you inclined plane. Inclined plane cannot be represented automatically in a 4-view drawing. I am sorry, 3-view drawing. If you add a 4th view, that is add an isometric or pictorial view, then inclined planes also can be handled. So, if you have a cube and one side is cut off, plan and then the elevated views look still simple. The side view shows you a slope. I can create objects which appear very complex in 3 views. If I take a cube and then join some corners, make a triangular thing, attach something else on top of it and put it in, it is still a technical illustration, only a trained fabricator or a draftsman will understand. Now come back to next level of this thing. We have the wireframe and surface modelers. Next slides explain each of them. Then we have constructive solid geometry or solid modeling. So wireframe surface modelers are still a little like the wireframe only, except that in the case of the wireframe, the highlighted edges are shown. Surface modelers take those edges, join the edges and make them, while rendering or while presentation, it makes it look like a, all the features behind the surface are hidden. So, in the very elemental form, you just need 3 points in space. You have x1, y1, z1, x2, y2, z2, x3, y3, z3, and then through an elemental space like this, a triangle can be drawn. Understand? No, any 3 points in space, and normally a flat triangle can be drawn. Using this, you can create complex surfaces. So one of them is, if I have two, I will put it here. If you have 2 straight lines like this in one plane, we can always join that edge and this edge and then try to make a surface. Now imagine it is twisted like that slightly. You can draw a surface, can be drawn in this immediately. So what is done is the surface is slowly turned in and make into this. The simplest way is take any point here, take any point here, make one triangle. That is as if we are to have a flat sheet like this. Here it is twisted. In reality, between any of these 2 vertices, we can make a fold. You have seen this? This is already a elemental triangle and a mesh with 4 vertices where 2 of them have been joined together to make a nice triangle. This is probably the starting point of all wireframe and surface modelers. Depending on the resolution or granularity of the mesh, you can make things look as if they are real. So in reality, this is a truly organic form. But in a representation of a CAD, you probably have one arc here, one more arc here, and what is called some way of creating the surface will be there. And all these, there is a beautiful depression here, and it's in 2 colors. And then another thing which is very, very easy to produce in CAD is it has a non-slip grip here made with a different material. So maybe it is just a sticker, maybe it is another material which is plugged inside. We have the various types of solid modeling, including constructive, boundary representation, hybrid, feature based solid modeling, parametric feature based, and dynamic. When we talk about parametric, the essential thing is saying sequence of assembly, how two things are tied up together, and bidirectional associative dimensions will be there. Meaning, if we have a bearing housing and a circular bearing has to go inside, we can tie these two surfaces, or you have a hole and then you have a screw or a plug can be inserted. We can tie these things together, and if we change something, dimensions will change, and we can make the other thing also change. Alternatively, at the command prompt, if you type the necessary dimensions, both of them will take the new, accept the feature. Subsequent thing is available, and then I will try to explain to you here. So, each of them separately has been explained. Again, I said it is taken from the engineer's handbook. In the simple 2D drafting, specific options to look for when choosing a 2D drafting package. I am sure some of you have used the Paint and Word or compatible software which is available in most computers. I am I have been given Windows as such, got used to it, but then I am sure Mac has better things, and then I won't say better, equally useful things, and then so much is there in the Linux also. Linux open software also it is there. In all of this you still have 2D objects. All we have is, if you have 2 points you can have a line, and then if you have more points you can put a very complex object, and then something called handles and beta splines, Bezier curves and all, that is a separate thing. Anybody who is interested, I will show you a book by Zayed, Z-E-I-D. You read the book. I couldn't read it because I sat in the class and I got it first hand. So, we have stuffs about splines, polylines, ability to define hatching and all that. The actual technical 2D drafting packages have these features also. What is a polyline? Hatching, complex boundaries, associative hatching, complete dimensioning ability. So, sometimes you just need to pick any entity like a line, and then automatically it takes what are the necessary features and give you various things. Like simplest thing what we can talk about is a dimension, and then something related is probably an angle, and you can have a true dimension of the actual entity, and you can have the dimensions in all the orthogonal views. There is an advantage and there is a disadvantage, which as you start using I am sure you will get it. The thing is, some of the old free versions which were available did not have these developed well. Eventually we have got a materials, bill of materials, BOD. Now 3D wireframe surface modeling, which as a second one there, you see here, right now they continue to be used, but they have been upgraded to the solid modelers due to the translation difficulties entailed with wireframe and surface models, trying to incorporate models in analysis or manufacturing software. A surface modeler basically just shows you a surface. It doesn't talk too much about what is behind the surface or what the surface is about. Like I have told you about it, I am sure this can be easily done in clay. Pat dough, any cookie dough or anything, and then let it dry up and then paint it and then also mask it and all that. Then you can't make out in a normal this thing whether it is solid or just a collection of surfaces. So that is the reason erstwhile simple surface modelers and these wireframe modelers have all grown up into genuine solid modelers. Advanced modelers utilize surfacing for creative freeform surfaces that simultaneously curve in 3 directions, especially for industrial design. This course was being offered in industrial design. So at that point, if you remember the second or third lecture, I showed you about an ink pot. Ink pot is just about an ink pot. I didn't want to repeat it, though I have the samples here. But then it is attached with a timer and then is attached with a proper writing instrument, and we have a new product. So these things in industrial design especially, this what started off saying, if you remember the first slide, we are talking about saying illustrating software is not so good for 2D because this has progressed so far and people are ready to pay for it. People pay good money if you want a proper software. People pay good money and get this industrial design software. Solid modelers can be much more powerful than simple wireframe modelers. Actual solid objects instead of wireframe. Since these parts are represented as solids, have volume and given density, have a weight and mass, computer can calculate many physical properties such as center of gravity and moments of inertia, can even be performed for irregularly shaped parts for which manual calculations would be difficult. Finite element analysis techniques used to perform stress analysis. So constructive solid geometry is about the next thing. We'll talk about it. The thing is saying you actually make solids which have elements almost like the grains which are distributed, and based on that various things like density and things can be calculated, which makes tremendous use in things like mold flow analysis. So if you have a aluminum casting and then the way the mold flows inside, physical properties of rate of cooling, rate of solidification, how a skin is formed when it meets a cold surface, how the material actually flows inside, full models are available. If you have the model and if you have the material and if you have the physical process, you can find out how the actual physically the material flows inside and how the mold can be designed, how many can be optimized in a cavity and all this. This is where the constructive solid geometry made sense.